Hello students, welcome to Emerson Digit Max. I am Ramalakshmi, Head Department of Mathematics. This video is going to be a learning of 7BMA2C2 sequence and series. Here we are going to have module 2 of unit 1. In this session, we are going to cover the topics, the definition of sequences and some examples of sequences, bounded sequence, monotonic sequence, and convergence sequence. Now let us start with the definition of sequence. Let us consider a function f from the set of all natural numbers to the set of all real numbers defined by f of n equal to an. When we take the values of n as 1, 2, 3, etc., we will have the image of that value in the real set as a1, a2, etc., an, etc. The values a1, a2, etc., an, etc. is called the sequences in or determined by the function f, and we denote it by within parenthesis an. So we read it as sequence an. The nth term of the sequence is going to be an. The range of the function, which is a subset of the set capital R, that is set of all real number, is called the range of the sequence. Now let us have some examples of sequences. If we define the function from a natural number to real number by f of n equal to n itself. So we will have, whenever we put n equal to 1, 2, etc., we will get 1, 2, etc., n, etc. So a1 is going to be 1, a2 is going to be 2, etc., an is going to be n, etc. Let us consider another function f from n to r. We define it by f of n equal to n square. We will have the values 1, 4, 9. That is 1 square, 2 square, 3 square, etc. So let us have the next example f from n to r given by f of n equal to minus 1 power n. So whenever we take the n value as odd value, we will have minus 1. Whenever we have the n value as an even value, we will have plus 1. So the sequence will have the terms minus 1, 1, minus 1, 1, etc. So from this example, we conclude that it is not necessary that the terms of the sequence are distinct. The terms may repeat. Here the range of the sequence is minus 1 and 1. The range of the sequence here is finite. The next example is the sequence minus 1 power n plus 1. Now it is similar to the previous example. Here we must have n plus 1 should be odd or even. If n plus 1 is odd, we will have minus 1. If n plus 1 is even, we will have plus 1. So here the sequence starts with 1 and then minus 1, 1, minus 1, etc. The previous example started with minus 1, 1, etc. So the range of this sequence is 1, minus 1. But note that the sequence minus 1 power n and minus 1 power n plus 1 are different. How? When we put n equal to 1, sequence minus 1 power n have the first term as minus 1. When we take n equal to 1, we will have minus 1 power 2 equal to 1 as the first term. Therefore, the sequence are different. The next example is going to be a example for constant function and hence constant sequence. We are considering the function f from n to r defined by f of n equal to 1. We have the sequence 1, 1, 1, etc. Such a sequence is called constant sequence. Here we are defined a function f from n to r by f of n value is going to be n by 2 if n is even, 1 minus n by 2 if n is odd. So let us put the value of n as 1, 2, etc. When I put n equal to 1, it is going to be odd. Therefore, it will give the result 1 minus 1 divided by 2 equal to 0. So, the first term of the sequence is going to be 0. Then when I put n equal to 1, I will get 1 by 2. When I put n equal to 2, I will get 2 by 2. That will be 1 and so on. So when we put the values, we are getting a sequence whose range is Z, the set of all integers. This is the function f from n to r given by f of n equal to n divided by n plus 1. So when we put n equal to 1, we will get 1 divided by 1 plus 1, that is 1 by 2. When I put n equal to 2, we will be having 2 divided by 3 and so on. So the terms are 1 by 2, 2 by 3, 3 by 4, etc. The next example is f from n to r given by f of n equal to 1 by n. So the values will be 1 by 1, 1 by 2, 1 by 3, etc. The next function is f from n to r given by f of n equal to 2n plus 3. So when we put n equal to 1, we will get 2 plus 3, 5. When we put n equal to 2, we will get 4 plus 3, 7 and so on. Now let us take any element x belonging to R. That is, x is going to be any real number. We define a function f from n to r by f of n equal to x power n minus 1. So when we put n equal to 1, we will get x power 1 minus 1. That is x power 0, that is 1. When we put x equal to n equal to 2, we will get x power 2 minus 1 x. The next term will be x square, etc. This sequence 1, x square, etc. x power n, etc. is called geometric sequence. The next sequence is sequence minus n. So we are given sequence minus n. Naturally, we will put n value as 1, 2, 3, etc. So we will be having minus 1, minus 2, minus 3, etc. minus n, etc. So this range of this sequence is going to be the set of all negative integers. This is an interesting example. Till now, we defined a function and from that function we found the sequence. We can also give the few terms initially and give a rule for finding the remaining terms of the sequence. In this sequence, we are defining a1 equal to 1 and a2 equal to 1. And we give the rule as an equal to an minus 1 plus an minus 2. So when we put n equal to 3, we get a3 equal to a3 minus 1, that is a2 plus a3 minus 2, that is a1. So we know a2 equal to 1, a1 equal to 1, therefore we get 1 plus 1, 2. When we calculate a4, that is going to be the sum of the previous two terms, that is a3 and a2. Therefore it is 3 and so on. So we get a sequence 1, 1, 2, 3, 5, 8, etc. That is, first two terms are given 1, 1. Third term will be 1 plus 1. Fourth term will be 1 plus 2. Fifth term will be 2 plus 3 and so on. This sequence is called Fibonacci sequence. Next example is, in the same way we are given that a1 is equal to root 2. And we are given the definition, that is rule, as an plus 1 is going to be root of 2 plus an. So when we put n equal to 1, a2 is going to be root of 2 plus root 2. When we put n equal to 2, we will get a3 equal to root of, I have to put 2 plus a2 value. a2 value is again root of 2 plus root 2. So root of 2 plus root of 2 plus root 2 will be the third term and so on. Now this exercise is left to you. Let us have a brief discussion on what is to be done in this exercise. You have to find the first 5 terms of the following sequence. So you will take the values of n as 1, 2, 3, 4 and 5 and you will write the first term, second term, third term, fourth term and fifth term. So the example H is given as f of n equal to n if n is odd, 1 by n if n is even. So we have a similar example. See that example and find the solution for this. Here you have to find the range of the sequences. For example, let us take the first example. First problem, sequence n. Here the terms of the sequence will be 1, 2, 3, 4, etc., n, etc. The range of the sequence is positive integers. In the same way, you can find the other ranges. Now come to the problem G. Here f of n is defined as n by 4 when within this parenthesis x denotes the integral part of x. For example, if I put n equal to 1, I'll get 1 by 4. I can write it as 0.25. The integral part of 0.25 will be 0. When I put n equal to 2, I'll get the value as 2 by 4, that is 1 by 2, that is 0.5. Therefore, its integral part is again 0. When I put 3, n equal to 3, I'll get 3 by 4 again 0.75, whose integral part is 0. When I put 4, I'll get 4 by 4, that is 1, whose integral part is 1 and so on. So you can find the range of these sequences. Now let us define bounded sequence. A sequence an is said to be bounded above if there exists a real number k such that an less than or equal to k for all n belonging to n. Then k is called an upper bound of the sequence an. So we have a sequence an. Suppose we can find a real number k such that all the terms of the sequence is less than or equal to that real number k. We will say the sequence is bounded above and it has an upper bound k. In the same way, a sequence an is said to be bounded below if there exists a real number k such that an is greater than or equal to k for all n, then k is called lower bound of the sequence. So let us take the sequence. Let us find some real number k in such a way that all the terms of the sequence are greater than or equal to that k. Then we will say that k is a lower bound and the sequence is bounded below. So if we can find two real numbers such that one real number is more than the terms of the sequence and another real number such that that real number is smaller than the terms of the sequence, we will say the sequence is bounded sequence. That is, a sequence is bounded sequence if it is both bounded above and bounded below. The definition can be rewritten as, we can say a sequence as bounded if and only if there exists a real number k greater than or equal to 0 such that absolute value of an is less than or equal to k for all n. So from the sequence, you take the terms, you take the absolute value of the term. If that value is going to be less than or equal to the founded k value, then we will say the sequence is both bounded below and bounded above. Let us consider the example 1, 1 by 2, 1 by 3, etc., 1 by n, etc. It is a decreasing sequence. The highest value of the sequence is 1. All the values of the terms will be more than 0. Therefore, the upper bound is going to be 1 and lower bound is going to be 0. Therefore, the sequence is a bounded sequence. And now let us consider the sequence 1, 2, 3, etc. All the values of the sequence are more than 1 or equal to 1, but we cannot find the real number k such that all the terms of the sequence are less than that particular value. Therefore, the problem has lower bound 1. It has no upper bound. Therefore, it is bounded below but not bounded above. Consider the sequence -1, -2, -3, etc., -n, etc. The terms are decreasing values. The highest value of the sequence is going to be -1. All the values in the sequence are going to be less than or equal to -1. Therefore, it is bounded above, but it is not bounded below. Let us consider the sequence 1, -1, -1, -1, etc. It is a bounded sequence. The upper bound is going to be 1 and lower bound is going to be -1. When we take any constant sequence, say 1, 1, 1, 1, etc., the upper bound is going to be 1, lower bound is going to be 1, and that term is going to be the constant term. Here is an exercise for you. The first exercise is going to be determine which of the following sequence given in example 3.1 are bounded above, bounded below, and bounded. We have defined sequences and we had some set of examples now. In that example, you have to find out which are all bounded above, which are all bounded below, which are both bounded above and below. The next one is going to be, you have to give examples for the following. The first one is, you have to find a sequence which is bounded above but not bounded below. Another sequence which is bounded below but not bounded above. Another sequence which is bounded sequence. And another sequence which is neither bounded above nor bounded below. The next exercise is going to be, you have to determine the upper bound and lower bound of the following sequences if they exist. Try it for your own. Now let us define monotonic sequence. A sequence AN is said to be monotonic increasing if AN less than or equal to AN plus 1 for all n. Sequence AN is said to be monotonic decreasing if AN is greater than or equal to AN plus 1 for all n. Sequence AN is said to be strictly monotonic increasing if AN less than AN plus 1 for all n, and strictly monotonic decreasing if AN greater than or equal to AN plus 1 for all n. Sequence AN is said to be monotonic if it is either monotonic increasing or monotonic decreasing. So what the definition says is, if you are going to have a sequence AN, if all the terms in the sequence are increasing, that is, the first term is the smallest term, the next term is more than first term, next one is more than the previous term, and so on, if it is called monotonic increasing. In this case, some terms may be repeated. For example, in the examples given below, if you take the first example, 1, 2, 2, 3, 3, 3, 4, 4, 4, 4. It is increasing, it is monotonic increasing, but not strictly monotonic increasing, because here we have 2 equal to 2, then 2 is less than 3, 3 equal to 3, 3 equal to 3, 3 less than 4, 4 equal to 4, and so on. So here it is an less than or equal to an plus 1. But we say an is strictly monotonic increasing if an is strictly less than an plus 1. For that, let us see the next example. 1, 2, 3, 4, etc. and etc. This is 1 less than 2, less than 3, less than 4, etc. Therefore, it is strictly monotonic increasing. A sequence to be monotonic, it is enough. It is either monotonic increasing or monotonic decreasing, right? In the previous definition, bounded sequence, a sequence is bounded sequence if it is both bounded above and bounded below. In this example, sequence an is given by 1, minus 1, 1, minus 1, etc. See, 1 is greater than minus 1, but minus 1 is less than 1, and again greater than minus 1, and so on. So we see that it is neither monotonic increasing nor decreasing. So we cannot say sequence an as a monotonic sequence. So we can say that sequence an is not a monotonic sequence. The next example gives sequence 2n minus 7 divided by 3n plus 2. We have to check whether it is monotonic increasing or decreasing. For that, we take the nth term and n plus 1th term. We can either find an minus an plus 1 or an plus 1 minus an. We have to find out whether the resulting value is more than 0 or less than 0. The result shows that minus 25 divided by a positive value. Therefore, the total value is less than 0. So we found that an minus an plus 1 is less than 0. So an is less than an plus 1. Therefore, we come to the conclusion that it is monotonic increasing. In the next example, sequence an is given by 1 plus 1 by 1 factorial plus etc. plus 1 by n factorial. When we take a1, it will be 1 plus 1 by 1 factorial. a2 will be 1 plus 1 by 1 factorial plus 1 by 2 factorial. Therefore, a1 is less than a2. Similarly, a2 is less than a3 and so on. Therefore, sequence an is monotonic increasing sequence. It should be noted that suppose sequence an is a monotonic increasing sequence, we will be having a1 less than or equal to a2 less than or equal to etc. So the smallest term in the sequence will be a1. Therefore, we can say it is bounded below, and we can conclude that a1 is the greatest lower bound of the sequence. Similarly, a monotonic decreasing sequence an is bounded above and a1 is the least upper bound of the sequence. Now let us see the solved problem. Show that if sequence an is a monotonic sequence, then sequence a1 plus a2 plus etc. plus an divided by n is also a monotonic sequence. We are not given it is monotonic increasing or decreasing. It is a monotonic sequence. Suppose an is monotonic increasing, then we have to prove that a1 plus a2 plus etc. plus an divided by n is also monotonic increasing. Without loss of generality, let us assume that sequence an is monotonically increasing sequence. So we will be having a1 less than or equal to a2 less than or equal to etc. an less than or equal to etc. Let us take the nth term of the required sequence as bn, and we mark it as bn equal to a1 plus a2 plus etc. plus an divided by n. In order to prove sequence bn is monotonic increasing, we are going to take the nth term and n plus 1th term. As I told you before, we can put either bn minus bn plus 1 or bn plus 1 minus bn. Here we are taking bn plus 1 minus bn. On simplification, we note that it is greater than or equal to 0. So the simplification part is going to be taking LCM of the two terms. and taking the terms as n times an plus 1 minus a1 plus a2 plus etc. plus an. We know that it is monotonically increasing. We know that a1 is less than or equal to an, a2 is less than or equal to an, etc. an equal to an. Therefore, it becomes greater than or equal to n times an plus 1 minus n times an. So on simplification, we find that bn plus 1 is greater than or equal to bn. Therefore, we proved that sequence bn is monotonic increasing. So instead of taking an as monotonic increasing, if we take sequence an as monotonic decreasing, we will get sequence bn also is monotonic decreasing. Here is a set of exercises for you. The first exercise is going to be giving example for monotonic increasing and bounded above, monotonic increasing but not bounded above, monotonic decreasing and bounded below, monotonic decreasing but not bounded below. The second question is going to be take the examples given in sequences and determine whether that sequences are monotonic sequence. The third problem is going to be determining whether this sets A to H are monotonic sequences. For this, you will take nth term and n plus 1th term. You will take either an minus an plus 1 or an plus 1 minus an. You will find out whether it is less than or equal to 0 or greater than or equal to 0. Accordingly, you will say it is monotonic increasing or decreasing. The fourth question is, if sequence an and bn are two monotonic increasing sequences, let us take increasing, the similar thing for decreasing also. Then we have to show that an plus bn is also monotonic increasing. So we can take the nth term of this sequence, that is an plus 1 plus bn plus 1 minus an plus bn, and we can take whether it is less than or equal to 0 or greater than or equal to 0, from which we can prove the result. The next problem is going to be sequence an is monotonic increasing. Lambda is a positive value, gives that sequence lambda an is also monotonic increasing. If it is going to be negative value, then sequence lambda an is monotonic decreasing. So try these problems. Now let us see the definition for convergence sequence. The convergence in mathematics is the property of approaching a limit more and more closely. That means when you have a sequence of values and if you find the limit value, if most of the values of the sequence is almost nearer to that limit, then we will say the sequence is convergent. So now we are going to see the proper definition of convergence. A sequence an is said to converge to a number L if, given epsilon greater than 0, there exists a positive integer m such that absolute value of an minus L is less than epsilon for all n greater than or equal to m. This means you consider the sequence an, you find the limit L. Epsilon is a very small positive value. You choose a positive integer m. So you can neglect the terms a1, a2, etc. up to am. After am, if you take any term from the sequence and find the difference between that term and L, its absolute value will be smaller than that small value epsilon. In that case, we can say the sequence converge to L. and we can write it as limit n tends to infinity of an equal to L, or sequence an tends to N. So girls, whenever we are given a sequence an, most of the terms in that sequence is nearer to a particular value L, we can say that sequence is convergent. To identify whether it is convergent, we take a very small value epsilon, neglecting the terms that are away from the convergence. The remaining terms should satisfy the condition that absolute value of an minus L less than epsilon. So we can write this as, if L is going to be the limit and epsilon is going to be that small variation, if we take the interval L minus epsilon and L plus epsilon, after neglecting the initial m terms, all the terms lie in the interval L minus epsilon comma L plus epsilon, we can say sequence an is converging to L. So the note says sequence an converges to L if and only if, given epsilon greater than 0, there exists a natural number m such that an belongs to L minus epsilon comma L plus epsilon for all n greater than or equal to m. This means all but a finite number of terms of the sequence lie within the interval L minus epsilon comma L plus epsilon. There is no definite method for finding the limit. We can, on seeing the sequence itself, we can guess the limit, and that limit can be attained by if finding the epsilon value properly and positive integer m correctly. Now we are going to prove the theorem. A sequence cannot converge to two different limits. That means if we are going to take a sequence an, we can say sequence an converges to L. That L is unique. This is what we have to prove. If possible, let us assume that there are two possible limits L1 and L2. They are distinct. These two are limits of sequence an. So by definition, we can write sequence an tends to L, tends to L1, as well as sequence an tends to L2. For the convergence, the main term or main sentence or main assumption we need is epsilon greater than 0 given. So we are choosing epsilon value that is greater than 0. That may be a very small value or little bigger value depending upon the sequence an. Now as sequence an converges to L1, by definition there exists a natural number n1 such that absolute value of an minus L1 is less than epsilon. But we are having another limit also. So we, instead of taking epsilon, we take epsilon by 2. Since epsilon is greater than 0, epsilon by 2 is also greater than 0. This is true for all n values greater than or equal to n1. Similarly, as an is tending to L2, there exists another natural number n2 such that absolute value of an minus L2 is less than epsilon by 2. This is true for all n greater than or equal to n2. Now, among this n1 and n2, we are going to choose the maximum value and we assign that maximum value the name m. So, we are taking m is equal to maximum of n1 and n2. Now, we are going to find the difference between L1 and L2 by taking absolute value of L1 minus L2. For that, we are adding and subtracting AM so that it is converted into two absolute values. So sum of two absolute values will be more than, that means a plus absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. Therefore, we get this is less than or equal to absolute value of am minus L1 plus am minus L2. By 1, we know this is less than epsilon by 2. By 2, we know this is less than epsilon by 2. So, we get this absolute value is less than epsilon. See, we have taken that epsilon is greater than 0. So, it may take a value 0.00001, or it may be taking some 0.1, or it may be taking a value 10. So, this is true for all epsilon value. So, if at all that epsilon value is going to be 0.00001, any value smaller than that will be possible only when this value is going to be 0. Therefore, we have L1 minus L2 equal to 0. So, we get L1 equal to L2. That is, the given sequence cannot converge to two different limits. Let us see some examples of convergence sequence. The first problem is, we have to prove that limit n tends to infinity of 1 by n equal to 0 or sequence 1 by n converges to 0. So here we are given that L is 0. So as per definition, we have to select the epsilon, a very small value that is greater than 0. So let epsilon greater than 0 be given. By the definition, we have to find the positive integer m such that absolute value of an minus L less than epsilon. Here our an is going to be 1 by n. L is going to be 0. So 1 by n minus 0, whose absolute value is going to be 1 by n, that should be less than 0. This value will be less than 0 if the n value is greater than 1 by epsilon. That means for all positive integers whose value is greater than 1 by epsilon, the condition absolute value of 1 by n minus 0 less than epsilon holds. Therefore, if we choose m to be a natural number such that m is greater than 1 by epsilon, then absolute value of 1 by n minus 0 less than epsilon for all n greater than or equal to m. Therefore, limit n tends to infinity of 1 by n is 0. In this problem, we are already given that limit n tends to infinity of 1 by n equal to 0. If at all it is not given, find the value of limit n tends to infinity of 1 by n. You just apply the value for n, which is bigger natural numbers. Start from 10, go up to 1000. So all the values will be reaching almost 0. So we can guess that by seeing the sequence itself, most of the terms of the sequence are nearer to 0. Therefore, 0 will be the limit. The next example is a constant sequence. A constant sequence 1, 1, 1, etc. All the values are 1 itself. Therefore, we are going to have the value converges to 1. Therefore, our L value is going to be 1. As per the definition, we are going to select a positive small value epsilon greater than 0. So, let us take the sequence as sequence an. So, sequence an takes the value 1 for all n values. So, we take absolute value of an minus the limit value 1. An is going to be 1 always. Therefore, absolute value of 1 minus 1, that is equal to 0 less than epsilon for all n belonging to n. Therefore, we have proved that 1 is the limit of this sequence. The next example is limit n tends to infinity of n plus 1 divided by n equal to 1. So as usual, we are going to select epsilon greater than 0. L value is 1 here. An value is going to be n plus 1 divided by En. So we can write n plus 1 divided by n as 1 plus 1 by n. So we are having this value as n by n, that becomes 1, and 1 by n as it is kept, and minus 1. So this 1 and this minus 1 gets cancelled. Therefore, we get absolute value of 1 by n, that is equal to 1 by n. This should be less than epsilon. As in the first problem, 1 by n will be less than epsilon if n is greater than 1 by epsilon. Therefore, if we are going to choose m to be a natural number greater than 1 by epsilon, we have absolute value of n plus 1 divided by n minus 1 is less than epsilon for all n greater than or equal to m. Therefore, limit n tends to infinity of n plus 1 divided by n equal to 1. Next example is limit n tends to infinity of 1 by 2 power n equal to 0. We take epsilon greater than 0. Our an is going to be 1 by 2 power n, and L value is going to be 0. Absolute value of 1 by 2 power n minus 0 is 1 by 2 power n. Now come here. We know that 2 power 1 is greater than 1. 2 power 2 is greater than 2. 2 power 3 is greater than 3, and so on. Therefore, we have 2 power n value is greater than n. When we take the reciprocal, we get 1 by 2 power n is less than 1 by n. Therefore, we have 1 by 2 power n is less than 1 by n. This should be less than epsilon. 1 by n is less than epsilon if n is greater than 1 by epsilon. Therefore, if we choose m to be the natural number greater than 1 by epsilon, we get absolute value of 1 by 2 power n minus 0 less than epsilon for all n greater than or equal to m. Therefore, limit n tends to infinity of 1 by 2 power n equal to 0. Next example is the sequence minus 1 power n is not convergent. So that doesn't exist an L such that absolute value of minus 1 power n minus L less than epsilon for all n greater than or equal to n. Contrarily, let us assume that there exists an L, right, such that for a given epsilon greater than 0, there exists a natural number m such that an value minus L value, absolute value of that less than epsilon for all n greater than or equal to m. We take m and m plus 1, and we have the nth term and m plus 1th term, right? So minus 1 power m and minus 1 power m plus 1. That is, we are finding the difference between am and am plus 1. Its absolute value should be equal to, we are adding and subtracting L, that is the limit. So we know that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. Therefore, this is less than or equal to this absolute value and this absolute value. Now we are having that this result is true for all n values greater than or equal to m. So for m also the result is true. For m plus 1 also the result is true. We get epsilon plus epsilon. We get 2 epsilon. That is minus 1 power m minus 1 power m plus 1 equal to 2. How we are going to write it? So let us take m value is going to be some 1, m equal to 1, then m plus 1 equal to 2. So Whenever m is odd, m plus 1 is going to be even. Therefore, minus 1 power m will be minus 1. Then minus 1 power m plus 1 will become plus 1. So, minus 1 minus minus 1. So, we have absolute value of minus 2 here. That will become 2. Suppose this is going to be even. Then this will become plus 1. This will become odd. Therefore, we'll be having minus 1 here. Minus of minus will become plus. Therefore, 1 plus 1 will become 2. Anyhow, we will get the value 2. Now we are from this, we are getting that is from this, we are getting that the left hand side is 2, right hand side is 2 epsilon. Therefore, we get 2 less than 2 epsilon. Cancelling 2, we get 1 is less than epsilon. But we have chosen epsilon greater than 0 is an arbitrary value. That means the epsilon value may be less than 1 also. It may be 0.1 also. It may be 0.001. It may be 0.00001. So 1 less than epsilon is impossible. Therefore, the assumption made by us there exists a L is wrong. Therefore, the sequence is not convergent. Now we are going to see the theorem. Any convergent sequence is a bounded sequence. We know the definition of convergence. That is, whenever we are given epsilon greater than 0, there exists a positive integer m such that absolute value of an minus L less than epsilon for all n greater than or equal to m. That L is called limit. And we know the sequence is a bounded sequence if it is bounded above and bounded below. After that definition, we had a note. That note says that there exists a real number k such that absolute value of an is less than or equal to k for all n. So we have to prove that. Now we are given the information that the sequence an is a convergent sequence. Therefore, we are taking that limit n tends to infinity of an equal to L. So, by the definition, given epsilon greater than 0, there exists m belonging to n such that absolute value of an minus L is less than epsilon, true for all n greater than or equal to m. This can be written as by taking this L value to the right hand side, absolute value of an is less than absolute value of L plus epsilon. This is true for all n values greater than or equal to m. So A1, absolute value of A1 may be equal to this value or greater than this value. Similarly, A2, A3, etc. up to am minus 1 values will be either equal to this absolute value of L plus 1 or greater than that. Only after m only we have am plus 1, etc. whose absolute value is less than L plus epsilon. Therefore, we are going to choose k as maximum of the values not involved in this. That is, the values less than m. Absolute value of a1, absolute value of a2, etc. Absolute value of am. Along with that, L plus epsilon. We are going to find the maximum of this value and we are going to take k as that value. Naturally, absolute value of an will be less than or equal to k for all n values including 1, 2, 3, etc. because we have chosen that k as maximum of these values. So we get absolute value of an is less than or equal to k for all n. This is the definition of bounded sequence. Therefore, sequence an is bounded. The converse of the above theorem is not true. What is the converse? A bounded sequence need not be convergent. For that, we are taking the example minus 1 power n. The sequence will have the values minus 1, 1, minus 1, 1. It is bounded because the upper bound is 1 and lower bound is minus 1. Therefore, it is a bounded sequence. But it is not convergent because its values are minus 1 plus 1, the alternating values. We have proved in an example that minus 1 power n is not convergent. Therefore, it is bounded but not convergent sequence. Here is the exercise for you. The first problem is prove that limit n tends to infinity of 1 by n square equal to 0. An is 1 by n square, L is 0. Therefore, let epsilon greater than 0 be given should be taken. Then you will take absolute value of 1 by n square minus 0. That is equal to 1 by n square. We know that n square is greater than n. Therefore, 1 by n square is less than 1 by n. We have to show that 1 by n is less than epsilon. 1 by n is less than epsilon if n is greater than 1 by epsilon. So, if we choose a positive integer m such that m is greater than 1 by epsilon, we will get this limit. In the same way, we can prove this second problem also. So, we are going to take 1 plus 1 by n factorial as an, L is equal to 1. In the third problem, an is going to be 2n plus 1 divided by 2n and L is equal to 1. So in the fourth problem, we are going to prove that these two sequences are not convergent. Already in the example, we have proved one problem. By taking the mth term and m plus 1th term, the result is not true. Using the same approach, you have to find the solution for this. Thank you for attending this video session.